All right, so we have been talking about polynomials, and now we are going to talk about exponential functions. So here's a definition of an exponential function. It has this form here, f of x equals a times b to the x. So notice that x, our variable, is in the exponent. So we call it an exponential function. So here a is a non-zero, so it can't be zero, real number called the initial value. Okay, that's what a is. B is any positive real number. Okay, so it has to be positive and it can't be 1. Otherwise, we get a really boring, just constant function. So what's the domain? Well, we can put any value in here for x and it's defined. So the domain is all real numbers. The range is going to be all positive real numbers. We'll look at some graphs and that'll make sense. If a is greater than or equal to 0, and it's negative if a is less than 0. And the y-intercept is 0a, okay? And the horizontal asymptote is y equals 0. So some of these, we'll talk about these more in the next section. We'll talk about the graphs of exponential functions. The important things for you to remember right now is that this is the initial value, and that b has to be positive. B has to be positive. It can't be 1. All right, so kind of in contrast to linear functions, here's the exponential function, and here's a linear function, right? So for a linear function, the growth rate is constant, right? From 0 to 2, 2 to 4, 4 to 6. We're adding 2 every time, okay? For an exponential function, we're multiplying. I don't want to move the cursor so that thing pops up. We're multiplying by the same number every time, right? We multiply by 2, 1 to 2, 2 to 4, 4 to 8, 8 to 16, right? So a linear function, we're adding the same value every time. For an exponential function, we are multiplying by the same value each time. So here's that same function, 2 to the x. So we can kind of see what an exponential graph looks like. And we can evaluate it at different values of x. So 2 to the negative 3, remember using properties of exponents, is 1 over 2 cubed, which would be 1 over 8, 1/4, 1/2, right? And we are increasing. And notice that the initial value, the place that it crosses is 1. The y-intercept is 1, because our initial value here, it's not written, is 1, right? Our a value in front here is 1, and this base is 2. So this base, 2, tells us how fast it's growing, right? That 2, we're multiplying, for every increase by 1 of x, we're multiplying by 2, because in this case, that is our base, our b value. And then we can plot it and see that it increases really fast. All right, so using this definition, which of these are exponential functions and which are not? Well, this is not, right? This is a polynomial because our x isn't in the exponent, right? Our variable isn't in the exponent. So this is not an exponential. How about this one? It is. We actually could rearrange this if we wanted using properties of exponents to make it look like a times b to the x. We have an expression with x in the exponent. It's exponential. How about this one? We've got a base. It's not negative, so that's good. X is in the exponent. Yep, this is an exponential. How about this one? Looks close because x, the variable, is in the exponent, but the base is negative. Can't happen. Okay, this might have other interesting properties, but it's not an exponential function. Okay, so let's just practice evaluating them. So if we had, here's an exponential function, our a value, our initial value is 5, and then our base is 3, and we're raising it to the x plus 1. Evaluate f of 2 without using a calculator. Okay, so just like any other function, we just plug 2 in for x, add those together, we use 3, we get 3. 3 cubed is 27, 5 times 27 is 135, right? Now, one thing just to be careful of with these, you have to use properties of operations, right? PEMDAS. You can't multiply 5 times 3 and get the right answer, right? You got to take care of the exponents first, and then you multiply by the initial value. Okay, so exponential growth. A function that models exponential growth grows by a rate proportional to the amount present. That's just a function. Because of the way the function is set up. So for any real number x and any positive real numbers a and b, an exponential growth function has this form. So a is the initial or starting value, and b is the growth factor. So this is like exactly what we just talked about. So one thing just to notice, they keep saying these are positive real numbers. So with polynomials, we started talking about complex numbers and imaginary numbers. They are like off the table for exponentials. Okay, we're only dealing with real numbers when we're talking about exponential functions here. All right, so here's another example. So let's say we've got two companies, A and B. So A has 100 stores and expands by opening 50 new stores a year. So is this linear or exponential? It's going to be linear because every year it opens the same amount, right? It's opening 50 new stores every year. And we could write a linear equation that has that form, right? It starts with 100 and then it has 50 more every year. Company B has 100 stores and it expands by increasing the number of stores by 50% each year. Okay, so the amount that it increases depends on how many it has that year. This is going to be an exponential function that has this form. Okay, our base, we're starting with 100 and we're increasing by 50%. So we could also write this as 1.5, right? And this is supposed to be to the x power. Sorry, that's to the x power. Like this. There we go. There's our function for b. So this just shows some graphs. So over time, you can see exponential growth is going to be much faster than linear growth. And you can see year by year, for the first 2 years, they're the same, right? But then exponential growth really takes off. Okay, so exponential growth is much faster than linear growth. All right, so let's talk about this, a real-world exponential model. At the beginning of this section, we learned that, well, we didn't read that, but in your book, it says that the population of India was about 1.25 billion in 2013, with an annual growth rate of about 1.2%. Right? So that's telling us that it's growing, how much it's growing each year is dependent on how many people are in the country already. So this is exponential, right? It's not like a set amount, like it grows by 1 million people every year or something. How much it grows depends on how many people it has that year. So we can write this as an exponential function. So 1.25 billion is our initial value. So we're saying the number of people times 0 is year 2013, right? So this is our initial value. And we can make our base 1.012, right? If it's growing by 1.2%, 1.2 is over here. That's the percent, right? So like in this one, when it was growing by 50%, it was 1.5%, 1 plus the percent that it's growing. Here, 1 plus 1.2% will look like that. All right. Okay, and T is the number of years since 2013. So what will the population be in 2031? Well, 31 is 18 years past 2013. So we'll just find P of 18, plug that in, put it in our calculator, and we get 1.549. So there's going to be about 1.549 billion people in India in the year 2031. All right, so how do we find equations of exponential functions? So we need 2 data points. Okay, we need 2 data points to define a function. So if we're lucky, one of the data points has this form. They tell us what the initial value is or what the y-intercept is. So in this form, we know that value would be a, and then we just need to solve for b. So we'll do examples of both of these. However, sometimes neither one is they won't give us this initial value. So we are going to substitute both points into this and solve a system of equations. We'll do an example of that. And then we know a and b, and we write the equation like that. So let's do this example. In 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180, and they tell us the population was growing exponentially. Write an algebraic function representing the population n of deer over time t. All right, so if we say that time t is 2006, we know our initial value, right? So we can start by writing the equation like this, right? 80 is our a value, our initial value, if we define t to be 2006. All right, so now we need to plug our second value. They tell us that in 2012, the population was 180. So our y value is 180. Our t value is 6, right? Because 2012 is 6 years after 2006. Okay, so now we just need to solve this. So 180 divided by 80, they simplify that. They get 9 over 4 equals b to the 6th. What do we do now? B is going to be raised to the 1/6 power. Okay, so b is raised to the 1/6 power. So that's going to be 9 divided by 4 to the 1/6 power. We put that in our calculator, and we get b equals 1.1447. Whoops. And here is our graph. And so I guess I didn't put the last thing in. So we just substitute that in for b up here, right? And this is what it would look like, our exponential growth. All right, so in this case, they gave us our initial 0, 80, our y-intercept value, okay? What if they don't? They just tell us find an exponential function that passes through these 2 points. All right, first thing we do is we just put in a and b, or we don't have a and b. We want to solve a and b. We put in these 2 values for x and y, right? So 6 equals ab to the negative 2, 1 equals ab squared. Okay, so we've got these 2 equations, 2 unknowns. All right, so let's start with the first equation. We're going to solve for a in terms of b. Okay, so divide by b to the negative 2. That gives us a, and then we simplify this to be 6b squared using properties of exponents. Okay, so here we have a as a function of b. Now we go to the second equation. Okay, 1 equals ab squared. We plug this in for our a value, right? So here's a. We put in 6b squared and simplify. Divide by 6. And now we solve for b, right? So divide by 6 and multiply, raise both sides to the 1/4 power. Put that in our calculator, and we get our value for b. So there we go. And then we have our value for b. We go back here and solve for a by just putting this in our calculator. And now we put it all together, right? So our a value is 2.4492, and b is 0.6389 to the x power. Okay, and here's what the graph looks like. So what did we do? We wrote our 2 equations. We solved one equation in terms of the other. Used one equation and solved for one variable in terms of the other. Plugged that into the other equation to solve for that variable, and then went back and substituted in to solve for the first variable. Okay, this is similar to what we do when we're solving systems of linear equations. So those are the steps. What if they just give you a graph? Well, you just have to be a little bit clever and find the 2 points that you want to use to make your equation. Okay, so they gave us this graph and said, write the equation. We need to find the 2 points that we want to use. So it's always a good idea, since we get to choose, to use the y-intercept as one of the points. So here's the general form. We can just look at the graph easily and say that, oh, a is going to be 3 because that's the y-intercept. And then we find another nice point. So let's see. Here's one. What did they use? x2, y12. That doesn't look especially accurate. I would use 2.5 and 18. I I would put in y for 18 and 2.5 for x, and then solve for b. So again, this doesn't exactly match their graph. Okay, but the idea is the same, right? You choose 2 points on the graph and use the same process as if they had told you what the 2 points were. All right, and finally, we can use our calculator to just do the hard work for us. So if they told us these 2 complicated looking decimal points, use a graphing calculator to find an exponential equation that goes through these 2 points. Okay, here's how you could do it. You go to Stat, Edit, and clear your lists. Okay, then you make your lists. Put the 2 and 5, the 2 x values in for list 1, and 24.8 and 198.4 in for list 2 for the y coordinates. Then you go to Stat, Calc, Exponential Regression, and press Enter. Okay, and it will tell you what your a and b values are if you didn't want to do it by hand. Okay, so then you'd know that your a value is this and your b value is this, and that would be a shortcut, or using technology to find your exponential equation.